Okay, welcome everyone in the room and online to the Dean's Frontiers Lecture 2025. My name's Jess Wade. I'm a Royal Society Research Fellow and Lecturer in the Department of Materials. The Frontiers Lecture is an annual lecture series run by the Faculty of Natural Sciences. The lecture highlights one of the faculty's departments each year, and this year the theme is physics. We are delighted to have Sir John Pendry, Chair in Theoretical Solid-State Physics here at Imperial, to deliver the lecture today. Before we start, I have a few housekeeping notices. There are no fire alarms planned for our in-person audience, so if the fire alarm sounds, please exit the building and head to the Dangle Plaza Fire Assembly Point, which is somewhere over there. Sir John has kindly agreed to answer some questions after the lecture, which have been collected from the audience, and they've been pre-submitted ahead of the lecture today, so we'll get to that after his fantastic lecture. I'd also like to briefly mention that the UK Metamaterials Network annual conference is coming up next week. The registration deadline for that is coming up next week. So you can find more details on the UK Metamaterials website if you're inspired by what's happening today. Finally, I would like to invite our in-person audience to join us downstairs in the Queen's Tower Room for a fantastic celebration and a drinks reception looking at some awesome research from the Metamaterials research community, and that's going on after the lecture, so if you just proceed downstairs to take a look at that. I would now like to introduce the Dean of the Faculty of Natural Sciences, Professor Richard Craster, who's going to give an introduction to our speaker. I really, really hope that you enjoy this lecture.
Well, thank you very much, and thank you, Jess, for welcoming our audiences here at South Kensington, and also welcome to those of you joining us online. I'm delighted to introduce our speaker, Sir John Pendry. And John, I hope you won't be embarrassed by me going through your history here, but John began his education at his local grammar school before continuing on to Downing College, Cambridge, where he underwent his undergraduate degree in natural sciences. He stayed on at Cambridge to complete his PhD, where he worked on the theory of low-energy electron diffraction with Volker Heine. Upon leaving Cambridge, John spent a year with Bell Labs in New Jersey, there writing the first of many of his books. After a brief return to Cambridge, John was offered a position as head of the New Theory Group at the Daresbury Synchrotron Radiation Laboratory. There, John's theory of EXAFS spectra developed into a more general theory of photoemission from the valence and conduction bands. After 6 years at the Daresbury lab, we were lucky enough to have John join us here at Imperial in 1981, where he has remained ever since. John spent some time working on the localization problem, which he describes as a peculiar and little understood transition in behavior between conducting and insulating states as the disorder is increased. And in 1994, he published his first papers on photonic band structures, enabling the interaction of light with metallic systems to be discovered. This led to his invention of the idea of metamaterials, which began a new phase in John's research career. John's work on metamaterials, of which we will hear in this lecture, has defined a new discipline within physics. Metamaterials answered the problem of how do we create negative materials with negative refractive index. It led to John's discovery of the perfect lens in a paper that celebrates its 25th anniversary this year, with well over 3,500 citations, as well as discovering the principles behind invisibility cloaking. His work now turns to light interaction with surface plasmons supported by metallic systems, and the transformation optics tool brings understanding to many strange phenomena in these systems, such as surface-enhanced Raman scattering. John's pioneering role in the field of metamaterials will lead to many advancements, or has already led to many advancements. And these are in 5G, 6G network technology, MRI machines, satellite communications, and much more, many of which is actually illustrated in the showcase downstairs. Some of these many uses are on display in those demonstrations, and as Jess mentioned, they're in the Queen's Towers room if you want to go to them afterwards. Indeed, it must be said that the lasting impact of his research will be felt by society across the globe for many years to come. And this has been recognized by his many accolades, most recently the 2024 Kyoto Prize in Advanced Technology in the category of Material Sciences and Engineering. Please join me in welcoming Sir John Pendry to deliver his talk, which is entitled Metamaterials, invisibility, and perfect lenses, a new world for electromagnetism.
Thank you, Richard. I hope I deserve some of the remarks that you've made. As you know, I'm going to talk about metamaterials. If you're going to make something or do something useful, you have to make it out of a material. And as far as light and electromagnetism generally is concerned, there is actually a shortage of the sort of materials that we may want to have. There are many things in optics which we know in principle we should do. No physics forbids it, but we cannot do because there are no materials available. And metamaterials are a way of answering that question in part. Richard.
Sorry, it's just flashed up with this software update. I'm a little concerned by that.
But I just got going.
And I'm rather hoping it won't come back.
Okay. Where was I? Right. Okay, so materials are badly needed in optics, and metamaterials have answered some of those questions, not all of them, but they've answered some very, very difficult questions indeed. So, talk in three parts. I'm going to tell you what metamaterials are, what they can do, and why they're useful. And then very briefly at the end, to just give an indication of what we're doing now and what the future might hold for metamaterials. So conventional materials comprise atoms, and they owe their properties to the properties of the constituent atoms. And if you want to alter their properties, basically you alter their chemistry. So if you want to make glass more sparkling, you add some lead to the glass, and that will increase the refractive index and make it more like a diamond. And the key thing about materials used in optics is the constituent parts, the atoms, are much, much smaller than the wavelength of light. So the wavelength of light makes an average over all the millions and billions of atoms within that wavelength. And so what you see is an average over many atoms. You don't see the individual ones. But there's a lot of space between the atom and the wavelength of light. There's 3 orders of magnitude, a factor of 1,000 or more. And so in that space, you can say, well, I'm going to not use single atoms or single molecules. I'm going to use something a bit bigger, something that I can engineer. And if you take a structure, which in the case of light might be 40 nanometers across, it's possible to engineer structures like that, change their shape, change their geometry. And in doing so, you can change their properties. So the idea of metamaterials is that you engineer a property using geometry rather than chemistry. And because the number of elements in the periodic table is limited, what chemistry can do is a great deal, of course, but it is limited. And by adding the dimension of geometry, which is almost limitless, you can do much, much more. So how do the atoms work to respond to light? Very, very briefly, atoms respond to light by invoking transitions between levels of the atom. And the response of the, yes, this does work. And the response of the atom to light, so this is the polarization of the atom, the way that the electrons move in the atom. And if the light has a low frequency, below the transition frequency, then the electrons move in the direction that the light is pushing them, and that's called a positive polarization. But something else can happen, which is going to be important to our story today, and that is if you move to frequencies which are higher than that transition, you get this negative response. It's a bit like a pendulum. So if you have a child on a swing and you just let the swing go, it will have a natural frequency with which it swings to and fro. If you want to push the swing, it's okay if you push it slowly, because it will go in the direction that you push. But if you try to do it too quickly, that sort of thing will happen with the swing going in the opposite direction to the way you push it. And that's true of the electrons in an atom as well. So this is perhaps one of the early metamaterials structures, perhaps the most famous one, the split ring structure, which is designed for use at radar frequencies, because we were working with the Marconi company at the time, which does radar. And the idea here was to produce magnetism without magnets. So this structure is made of copper, and it's a ring. So if you put a magnetic field down the middle of the ring, that will induce a current flowing around the ring, and current flowing in a ring makes a magnetic moment. So without any magnetic material, you've actually produced a magnetic response to a magnetic material. But there's more to this story than that, because if electrons flow in a ring, that ring amounts to an inductor. And I've done something else in this design. I've split the rings. So the electrons can't go right round the ring. And in order to complete the circuit, they have to jump across this gap here. And they do that through the capacitance of the gap. Now, every undergraduate in physics will tell you that if I put together an inductance and a capacitance, I get a resonance. And that, indeed, is the... What's going on there? Right. Anyway, and that is the resonance which this ring shows. And you will note its similarity to what the atom does. Okay? But this is doing things that an atom can't. So an atom has virtually no magnetic response. This ring has a lot of magnetic response. And there are other structures that we looked at which produce electrical resonances and so on and so forth. And I'll get to those in a moment. This was the paper where I introduced these ideas to the PEX-1 conference in Laguna Beach, and that was in 1999, a while ago now. And there you see the split ring structure that I've just shown to you. Since that time, the idea caught on for this reason that I said, that optics and electromagnetism generally are quite short of materials. So if there is the possibility of a new sort of material, people tend to pounce on it. And I marked some of the key events here. We're now up to about 3,000 or 4,000 papers a year, and it seems to be still growing. This is the 1999 paper on split rings. By the way, we didn't call them metamaterials in those days. The name was invented round about here, and it caught on for some reason. So that's the paper with the split rings. Then in 2000, two things happened. One was that in San Diego, the group of David Smith was able to create a material using our designs which had a negative refractive index. And that was something people had sought for many years. I'll talk about that. And the other thing was that when I became aware of negative refraction, I discovered that it could be used to make a lens, and a lens that was perfect. And I got into a lot of trouble for that. Somehow I came out of it not quite unscathed, but in one piece. And then we used some of the technology which we've been developing to design a cloak of invisibility. And of course, hordes of people are interested in that, courtesy of J.K. Rowling. And that gave another boost to the topic, and the thing grew. And one characteristic of this growth as it goes on is that it's not been confined to physics. A lot of other disciplines came in and had a look at what was going on, and it spread out into engineering and so on and so forth. And this slide gives you an idea of where it's gone. Not on this slide, and it should be, is the fact that it actually goes out into acoustics as well, and people are adapting these structures to do things in acoustics which were very difficult before. This is the first realization of a metamaterial split ring structure. It was done by Mike Wiltshire in 1998, just before the Laguna Beach paper. And one of the reasons that this idea of function through structure caught on is it's actually, at least as radar frequencies, very easy to make these structures. In fact, Mike didn't make the structure. He made a drawing of what he wanted, and he sent it off to a printed circuit board company who then sent this thing back through the post. So the dimensions here are about 1 centimeter, and this is resonant at about 10 gigahertz. So it has a magnetic response around those frequencies. Quite soon after that, people were able to develop structures which worked at higher frequencies. So this is work in the near infrared, which is a much higher frequency. It's near visible, it's near the telecoms sort of wavelengths. And it's a so-called fishnet structure. It comprises silver layers interspaced with a dielectric, and it's a resonance structure, and it's actually designed to give negative refraction. It was done in the Chang Zhang's group in Berkeley. So things can be done on all length scales down to about 1 nanometer now, a bit more maybe. Now, negative refraction has been mentioned several times, and this is a photograph of Victor Veselago, a lovely man, a great Russian bear of a man, and sadly he passed away a few years ago, but not before his vision had been realized using metamaterials. And Victor was the first person to really take negative refraction seriously, and he wrote a long paper in 1968, and the first thing he did is to tell us how we should make a material with a negative refractive index. And the recipe is simple. All you've got to do is to make something with an electrical response and a magnetic response, both of which are negative. And in those slides I've showed you before, I've shown you that sometimes it's possible to have a negative response if you're the right side of that resonant line. And then he went on to indicate all sorts of other things and why you might think negative refraction, well, you know, we do positive numbers, we do negative numbers, we do imaginary numbers as well. What's so special about the refractive index going negative? And that was my first reaction. And then I started realizing that if you're too blasé about it, you start saying silly things which can't be true because it contradicts this and that. And I'll show you some of them. So here's the first one you bump into. Now this shows a light ray entering a material with a negative refractive index, -1 in this case. And because the refractive index is -1, this refracts the wrong side of the normal. Okay, positive refraction, the light will come out this side. Negative refraction, the light comes out that side. So that's all fine. I should also point out that associated with waves are actually not one velocity, but two velocities. There's something called the group velocity, which is the velocity with which a little packet of waves progresses. And then inside the packet, there are waves themselves, which comprise the light or what have you, water waves, it's just a general thing. And the velocity with which the waves inside the packet travel is the phase velocity. Now, in ordinary materials like glass or air, they're the same, but they don't have to be, and they're definitely not the same in negative refractive index materials, because the wave vector, which describes the direction in which the waves are going, is this quantity here. And it's the same as the ray vector in vacuum. But there's a very strict conservation law, which is a law of mathematics, not a law of physics, which says that if you have a wave vector like this, then its parallel component inside the medium must be the same as it is outside. And you can see that the only way that you can satisfy that rule is to have a vector pointing this way. This vector on this side of the normal can never have that parallel component. So you can't have the wave vector pointing that way. And so this is an extreme example of the wave vector and the ray vector being quite different. And that has the consequence that if I have a wave packet here which is headed in this direction, and then I look inside that, the waves are rushing backwards trying to get out the other side. And that's just one of the many strange things that negative refraction is associated with. This is the first structure showing negative refraction. At the Laguna Beach meeting, I met David Smith and Shelley Schultz, and they were very keen to make some of these split rings. And they said, did I mind? Of course I didn't. I was delighted. And you can see that, although they squared it up a bit, this is recognizably a split something or other. And that ring, as I showed you, has this negative response here if you go to high enough frequencies. Now, something else which is difficult to see, but is indeed on here, is a wire. It's actually on the far side of that circuit board, but can you see a wire there? Now, that wire has an electrical resonance, and it too is designed so it has a negative response at the same frequency that the ring does. Bingo. Veselago's work in 1968 attracted an enormous amount of attention, and he did a lecture tour of the States, and people got very excited about it. And then it all fizzled out because he could not find, and nobody could find, and nobody has found, a naturally occurring material in which both epsilon and mu are negative at the same time. So there's no naturally occurring refractive materials with a negative refractive index. So that was the first structure, and there's a lot of interest in David's work, and it sparked a whole, oops, yes. Sorry, is that, yeah. Okay, so we have these materials which already at this very early stage, just after we announced the world, we're doing things which were impossible before. And there are many more things they can do beyond negative refraction. So the question was, do we have a design tool for these materials which can do many, many more things? The old design tool is the Snell's law, showing things refracting at an angle at the surface, and it works in the ray approximation. The alternative to that at the time was to solve Maxwell's equations, which is quite an effort. They're beautiful equations and they're exact. But what we wanted to do was to create a new vision which was beyond the ray approximation, exact to the level of Maxwell's equations, and works instead of the rays are an approximation, of course, to waves, but work with the field lines instead of the rays, and will be able to handle sub-wavelength optics, which is something which negative refraction introduces to in a big way. Now, we took inspiration from this man, and one of the things he told us was that the right way to think about gravity is not, as Newton did, as action at a distance. The right way to think about it was that a massive object like the sun, or even more massive objects like a galaxy, actually distorts space around it. Einstein thought of space as a sort of bit of rubber that could be stretched by very massive objects and distorted. And so it's natural to think that if a distorted space is distorted, it not only has influences on the orbits of the planets and so on and so forth, it will also influence the way light moves through it. So light moves through space, and if space is distorted, then the light's direction is going to change. And indeed, that prediction is one of the foundations of general relativity. Arthur Stanley Eddington in 1919 made this observation of the displacement of starlight as it passes the eclipsed sun. You can only see stars near the sun when you have an eclipse. So what was observed was that the light from, it's going the wrong way, isn't it? From the star is bent around the sun, so you think the star is there. And so this angle between them, which actually is very, very small and hard to see, is an indication that Einstein was right and that gravity does affect light as well as massive objects. I can't resist showing this other beautiful picture because it sort of brings to mind the cloaking I'll talk about. This is a picture from the Hubble telescope, a very, very massive red galaxy, which you see in the foreground here. Behind it is a blue galaxy, and you shouldn't be able to see the blue galaxy if light traveled in a straight line, but it doesn't. The massive red galaxy has a lens-like field around it, which diffracts or refracts the light from the blue galaxy, so you can see it. And in fact, gravity, a distortion of space, behaves like a lens, and in some sense, it changes the refractive index of space. You can think of it like that in a very simple way if you want. And so we took hold of this, and one thing we realized and contributed to this idea was that if you think of space as a rubber sheet or a block of rubber that can be shaped and distorted, and you think of a ray of light as something which is embedded in that, or a field line or what have you, any conserved quantity, then we realize that that ray of light is nailed to that bit of rubber. So if you stretch the rubber and distort it, you carry that ray of light with it. And I've tried to illustrate that here. So what I'm trying to do here is to design some structure in which I want the rays of light to go on this trajectory here. And the way I've done it is not pulling on the ray itself, but stretching this rubber sheet. Okay, a bit of space here. And now I make the analogy between the metric and the parameters of Maxwell's equation. I turn to Einstein and say, hey, Einstein, I want this light to go here. I can give you a coordinate transformation, a transformation which takes this coordinate system to that one, and please apply your formula, and here are the values of epsilon and mu that you need to make the light go in that direction. So very simple idea, but quite powerful, and I'll show you why. So we wanted to show people, I didn't want to go to town and say to people, hey, here's a formula, it's jolly useful. You're asleep already if I say that. Yes, we're showing formulae. But if we said to people, we can make something invisible, because that's what it can do, then people would sit up and take notice. And not just people in our field, people in other fields who didn't know about this metamaterial stuff and started to say, hey, maybe this is interesting. And it worked. So what do you have to do if you want to make something invisible? Everybody likes Harry Potter, but I prefer Peter Pan. His statue is over there in Kensington Gardens. And what did Peter Pan do? According to J.M. Barrie, he was a little boy who lost his shadow. Now, if you're going to make something truly invisible, it's not enough to paint it black, because if it's black, it still has a shadow. And the trick is to get rid of the shadow. And of course, J.M. Barrie wrote the story, and Peter Pan lost his shadow. What Barrie didn't realize is that if he lost his shadow, Peter Pan would be invisible, and therefore not part of the story anymore. However, so that's what we're going to do. We make Peter invisible. How do we do it? Well, first of all, we have to define a central region here in which we can hide anything. And in order for you not to see what's in there, any light which enters this cloaking region has to be diverted away from that central region here. Furthermore, you mustn't lose track of the light. You've got to be aware of where it came from, because you've got to return it to exactly the same trajectory as it would have had were the cloak not there. How would you solve that problem? Because you've got to solve it. You've got to have a material in here which solves it, not just for this ray, but for that ray coming here at any angle whatsoever. It's a nightmare of PhD projects. So how do we do it? Well, we start off with a bit of rubber, a bit of space, and I put my finger in the middle and I make a hole. And then I stretch the rubber so it's all squashed into this cloaking region here. It doesn't matter how I pack it in, but I push it out of the central region here. Remember, if I move space, I move the rays of light with it. So all the rays of light are now traveling in this region here because I push them there. I push the space there, and the rays of light have no choice other than to follow what the space does. But there's more. Because although I've heavily distorted this region of space here, I've done nothing to the space outside. If I don't mess with the space, I don't mess with the rays. So this is the simplest form you could imagine of squashing stuff into the cloak. And then you can plug that into the Einstein thing I showed you before, and out come the refractive index that you need to do that. And this is what David Smith did. So when David heard about this, the talk I gave in San Antonio to DARPA, he immediately started his team to make this stuff. And it's a long story, but a beautiful one. And within a few months, they'd actually designed this cloak out of metamaterials. They're not quite the shape that they started off, but it's recognized to be a ring, okay. And you can see that the ring refractive index is graded in exactly the way that the formula says it should be. And then David went on to do experiments and demonstrate that the rays of radar waves, of course this is radar frequencies, follow the trajectory that they should do. So now I want to move on to the refractive index, negative, and Veselago's lens. Veselago realized that his lens could focus light, and you can just show that with a ray tracing experiment. You can have negative refraction here, and because the light is bent the wrong side of the normal, it naturally comes to a focus inside the medium. In fact, it comes to two foci, because when it comes out, there's another one outside here. And that was registered as a curiosity. We've got lenses, why do we need another one? But there's something awkward about lenses that I've alluded to before, which is that light can't see anything less than a wavelength. It can't see the atoms in a block of glass. And most importantly, in your microscope, you can't see anything much smaller than the wavelength of light, unless you have a very special microscope indeed. And that's frustrating because that's the level of resolution when you're beginning to see inside a living cell. So it's very annoying to biologists that our microscopes can't resolve anything better than that. And indeed, there have been Nobel Prizes awarded for microscope technologies to extend the resolution of microscopes. And they work very well, but they're very expensive. Now, why is it so that light can't see something so small? In fact, it can. So if an atom emits light, near that atom in its immediate vicinity, the electric and magnetic fields reveal all the details right down to the nanometer level. Light can see almost anything if you get close to the object emitting the light. But the problem is that there are two sorts of light. There's one called the far field, because that's the light which actually is free to escape from the atom and travel as far into the universe, if you like. And that's the light which you collect in your microscope and you focus to an image. But it's limited by the wavelength of light in vacuum or in air or whatever your microscope works in. But there's another sort of light called the near field, which hangs on close to the atom and never leaves it. And it's teasing out this near field, which is the challenge for a microscope if you want to break this very rigid law, which was very rigid so far, called Abbe's law. And it was thought that Veselago's lens obeys Abbe's law, but it turns out that it need not. I showed in the year 2000, one rainy weekend in London. I was head of department at the time, so I had other things to do. I did all my research at weekends. Stefan, where are you? Our head of department. And I realized that this lens could, in fact, if you built it right, resolve everything. It was perfect. And I was amazed and embarrassed because I knew if I published that conclusion, a gang of wolves would descend on me. I did publish, and they did. But the wolves were driven off, and the conclusion is accepted. So how does that work? Well, I'm going to do an experiment here. Beware, because I'm a theorist. They're supposed to put my... Can you do my picture up there? Of course, you can't see what I'm doing otherwise. Have you got a camera? Then everybody online can see what I'm going to do. I thought I'd fix this. If you don't do it soon, I'm going to do it without you guys. Okay, so put your glasses on. We can't get a magnified view. They've gone to sleep up there. It happens in my talks. So what I'm going to do is I'm going to make a Veselago lens. I'm going to make a piece of negatively refracting index. And I'm going to do it this way. So as before, when I started with the cloak, I'm going to start with a piece of flat space, okay? And I know that if I squash space, according to Einstein, I'm going to make it more refracting as part of his theory of general relativity. So I'm squashing space. Okay, so this, can you see this middle bit here? It gets more refracting as I squash. And then as I squash harder and harder, and I get to this point where I've just squashed the hell out of it, the refractive index goes up to infinity. And in mathematics, if something goes up to infinity, if you do it some more, it comes out at minus infinity, the other side. Okay, so I'll do it some more. And now we have a piece of negative refracting index. And I go a bit more, and it's not minus infinity, it comes down, and then I've really squashed it, so it's almost back on itself. And there you have a piece of negatively refracting space. Now let's ask what this piece of negatively refracting space is going to do to light. So let's say there's an object here, and the light passes the object. It sees the object there, and then the light goes round. And remember, the phase vector reverses, so in a negative refractive material, it goes back along this bit of space, and it passes the object again, the identical object, according to Maxwell's equations that it saw before. And then it goes on to the edge of the lens, and it comes back, and it passes the object, the identical object, a third time, and then it exits. And so that explains the lens at the level of Maxwell's equations according to the bit of rubber space. But isn't that really strange? So think about it a bit more. You've done something really weird to space here. You've created a piece of space with 3 manifolds. Okay. Now imagine that you sat on one of those manifolds. There's a copy of yourself here and here. And just amongst yourselves, after the lecture, please, try thinking through the logic of that and how you're going to not contradict logic by things which can and cannot happen under those circumstances. And those, thinking about that, applies some of the rules which negative refraction has to obey. Because, of course, it has to obey the rules of logic. So that's another surprising thing that comes out of metamaterials and negative refraction. I think I have time for this bit. Yes, so what you ideally want to do to make a perfect lens is to have negative mu and negative epsilon. Unfortunately, for visible light, even with metamaterials, negative mu is extremely difficult, and even if you could do it, it would be very lossy, at least at the present moment. So I suggested that there's something called a poor man's super lens, and it works like this. So you have to think of light as a dance. It's got electric and magnetic fields inside it, and they dance around one another. So the electric field goes to a magnetic field, goes to an electric field, goes to a magnetic field, like that. And the step of the dance is the beat of the dance is the frequency of the light. And the step of the dance is the wavelength. And it takes half a wavelength for the electric field to turn into the magnetic field. Now, you imagine an atom emitting some light, and it does so through an electrical transition between the two levels. So it emits electricity. And it's only much later that that electricity turns into magnetism. So if you always stay clear to that atom within half a wavelength, let's say, you don't really see any magnetic field, so you don't care about it, and you only care about making epsilon negative. We've got lots of negative stuff. It's called a metal, and the best metal is silver. And here is the realization of my suggestion by Nicholas Fang, who's now a professor at MIT, but was at UCB, a postdoc with Zhang Zhang. At that time, they missed his G off for some reason. So here's the lens, silver, negative epsilon. Here's a spacer, and they're looking at this thing here, which is a grating, and the word nano written in chromium. And you can't see it with a microscope because it's too small. So there's a photoresist here, and then they strip that off of the experiment, and you show resolution, which is at a sixth of the wavelength, which is more than you get with a microscope. Whoops, what happened? There's a slide. Ah, yes, great. So, did I miss another slide? No. So, more spectacular is this word nano. So, if you don't have the lens there, this is what you see. And then you put the lens in there. It's like putting your specs on. And you can see that from the resolution plot here, which is a trace along one of these letters. And now, in the final moments, I want to tell you about some of the things that Metamaterials have done to help society. So there's a whole list there, microscopy, imaging, cooling, SATCOMs, comms, security, stealth, and so on. But instead of reading out the list to you, I'm going to show you some examples of what people have done with metamaterials. So here's some work from UCSD, Xiaowei Liu, a friend of mine. And he's using a metamaterial, a hyperbolic metamaterial. Hyperbolic, it means that it's half negative and half positive. Don't have time to explain that, but it is. So here's some biological goo. And this is the resolution which you can compute with an ordinary microscope. Here's a length scale, 2 microns. So you see the resolution is about half a micron. And then you use Xiaowei's hyperbolic stuff, and you can see he gets much better resolution now, probably about a tenth of a micron, something like that, or a bit less, actually. So that's one thing, super resolution microscopy. Other thing is very thin lenses. Now, these aren't super resolution at all. They just have the same resolution as an ordinary lens. But instead of using a bit of curved dielectric like glass, to refract the light, they use a principle that instead of having a thick piece of lens, they have a thin piece of lens, but with a higher refractive index. They're called graded index lenses, and they can be flat. And this one is jolly flat. It's a fraction of a micron thick, and it's made by the Capasso group in Harvard. And these resonant elements, which are the vestigial remnants of the split ring, I might say, are tuned so there's a higher refractive index here in the middle there towards the edges. And that achieves focusing, very good focusing, they claim, but with something that's a fraction of a micron thick. That was for use in the infrared. This technology has advanced since I made that slide. And here's a product from United Microelectronics of a meta lens working in the visible. And this is a piece of silicon, I think, that they've made here. Very, very thin. Global warming is an issue. Metamaterials can help a little bit. So my friend Xiaowei Yin, now in Hong Kong, has invented this stuff which can cool a space without using any power. So the idea is that, first of all, we've got to get rid of any sunlight that might enter the building and warm it. So this metamaterial sheet, which, by the way, can be made by roll-to-roll manufacturing, you can see it's already pretty big. You can make sort of meter-long bits of it. And it's highly reflecting to sunlight, so that the sunlight doesn't get at your building and doesn't have a chance to heat it. But more than that, it's designed so in the infrared, where the heat is, it's a very good emitter. And so overall, it's been demonstrated that it's got a cooling power of 93 watts per square meter under direct sunshine without any power input. And I believe it's been installed in an airport in Singapore. I can't vouch for that, so I'm told. Metamaterials are highly reconfigurable, and they can be tuned to have different properties. So if you make an aerial out of them, which is directive, you can alter the direction in which that aerial is pointing, and that is important if you want to communicate with a satellite. Now, that can be done already through what are called phased arrays, which involve a lot of elaborate and important expensive electronics, and it's heavy, by the way. And this is just a sheet of those structures I showed you, but with the addition of a diode to each one of them, which makes it tunable, so you can point it where you like. I don't have time to go into it, but there's a huge interest in the 5G and 6G. Already in your cell phone, there's some metamaterials helping the receiving areas and so on. In 6G, it's going to be an even bigger presence as the communication powers of 6G are much greater than 5G. MRI, the challenge in MRI is to pick up the very, very weak and sensitive signals, magnetic signals from molecules in the body, which give you the MRI image. And the quicker, the better, and the more noise-free you can do that, the sooner you're out of that horrible clanking MRI machine. And I'm sure some of you have been in one of these machines and you don't want to stay there very long. Here's Richard Sims. Where are you, Richard? Somewhere in the audience. I saw you a moment ago feeding his test equipment into an MRI experiment. And last but, well, penultimately, actually, it's not last. I did mention that this idea of metamaterials is going beyond electromagnetism. It's going into other fields which have to do with waves. It's even going into earthquakes. But let's stay with acoustics for the moment. And Ping Sheng, who was a professor in Hong Kong and is now in Cambridge, he suggested that you could get one of these resonant elements. Remember the resonant elements, the atoms, the split rings, and so on? This is an acoustic resonator, and the way he's made it is to take a rubber membrane, and in the middle of it is a little weight. And you can imagine that if you push that weight, it wobbles. It's a resonant structure. And if you put them together, you can do very interesting acoustic things with them. One of the things you can do is to make a whole sheet of these things, which you can wheel around on a trolley in a hospital, which will absorb any sound instant upon it, so that behind it you have a silent zone. And this is manufactured by a Bristol company, I think. And the idea is that you can use this to screen seriously ill patient in a ward or other people, not only from the lights, but also from the sounds which go on, which can be very disturbing. And then we have mechanical metamaterials. So you might want some interesting mechanical properties. This is, I think it's called auxetic or something. Anyway, it has a negative Poisson's ratio, and what that means is that whereas with an ordinary material, you squash it this way, it comes out that way. This material, you squash it this way, and it goes in that way as well. Yes, you can make this with metamaterials. So what about the future? We started late, so I have 1 minute, I think. Very quickly, what we're doing now is extending the concept of metamaterials. So you can structure materials in space, and we've spent a lot of time doing interesting things with that. But you can also structure them in time. You have to structure them very finely in time, because unless you do it on the sort of time scale that the light is vibrating, then you don't have much effect. But if you can do that, and Riccardo Sapienza's group in physics is experimenting with ways that we might use to do that, then you can enter a new world, because energy isn't conserved, so you can amplify light. Of course, you break time reversal symmetry, which is something people want to do for topology and so on and so forth. You can do extreme compression of radiation. And in some of these structures, in which you can induce a singularity, that singularity has similarities with the singularity in the black hole, which occurs at the Schwarzschild radius. And this singularity, just like the Schwarzschild singularity, emits photon pairs. It emits Hawking radiation. And Hawking radiation is never seen. Some people will think it never will be seen, because it has to escape from this massive black hole, and it's shifted so far into the infrared that it's terribly weak when it gets out, and so we probably won't see it. So the hope of seeing Hawking radiation rests on laboratory analogs, and these time metamaterials, one of the things they may do is provide a route for seeing finally Hawking radiation. So with that, I leave you with a summary, and I believe I have to answer some questions now. Thank you.
We can go and take a seat over here.
Okay.
In our nice little area for our 5 minutes of questions. And thank you so much for that incredible lecture. It must be really amazing to see these kind of theoretical predictions become realities and inspire hundreds of thousands of papers and patents and everyone in the room. As we anticipated, we had a lot of questions coming in, so we've selected a few, and it was amazing to see the range from kind of professors, emeritus professors, through to primary and high school students. So there's quite a range to these questions as well. I'll start off. Physical phenomena that are possible in theory, like negative refractive index, can take some time to reach experimental implementation. As a theoretical physicist, do you ever have to draw the line between we'll be able to make this in several years and we won't be able to implement this in my lifetime?
It's an excellent question that all theorists should ask themselves. And I give as an example what I spoke of right at the beginning of the talk, when Victor Veselago first theoretically proposed negative refraction. And it really did fizzle out when you couldn't find this stuff. Fortunately, Victor had a long life, and in his 80s, he was able to attend conferences where people were showing specimens of his negatively refracting material, and that was a great joy. But wouldn't he have had a happier life if they could have done it right there and then? He could be sitting here giving this lecture.
But it shows you that interdisciplinary part, how important that's been for your science, these engineers who've come on board to try and make these materials.
Yes.
It's incredible. Sorry, that was a rogue contribution from me, not an actual question. Okay, now for a slightly more funny one. What is your favorite state of matter and why?
I was going to say a glass of wine, but
that's for after the lecture.
Favorite state of matter? Okay, I think it must be water, because it does such inexpressible things with light. Have you looked at the surface of water? I've lots of videos of I have a little apartment down on the coast, and we look out on the sea, and it has various moods, and in some moods the sun actually sparkles. So water's a real favorite because of my other favorite, which is light, and it can do wonderful things with light.
And everyone can play with it at home without needing these fancy microscopes or lenses.
Yes.
Which is great. Okay. If you were starting your career today, which area of physics or another science or engineering would you focus on?
Yes. Well, I should say metamaterials, but I won't, because metamaterials is not a discipline. It's an area of research and engineering which comes about created by people who've studied very, very carefully the basic disciplines, such as classical mechanics, quantum mechanics, and so on. So if I was starting again, I would look at an idea I've been interested in for a long time and not really done much with. And it is the relationship between quantum mechanics and information. So information is a very nebulous thing. People believe that you cannot destroy information, that it is a conserved quantity, like, well, I won't go into details. But if you think about other conserved quantities like mass, charge, spin, and so on and so forth, with every conserved quantity, you can say there's some mass and it's here. And if it leaves that place, there's a current associated with it that flows away. Now, you can't pin information down like that, and that's to do with the non-locality of quantum mechanics. Information is neither here nor there, it's everywhere. And there are lots of paradoxes to do with that. And years ago, people realized that there were these paradoxes, but there was so much to do with quantum mechanics that, as Feynman said, shut up and calculate. And that's what people did for years. But now, we really have to turn to the question of what is quantum mechanics, a true interpretation of it, and what does it have to do with information? Because we're being flooded with information, and we're going to have to take it very seriously at the quantum level. Sorry, a long answer to a small question.
No, that's an absolutely fantastic answer, and one that aligns with the fact that this year is the International Year of Quantum Science and Technology. So hopefully that will inspire everyone to contribute to these big questions. So kind of final question now, and I think this is going to be a very hard one for you because you're very passionate about all the examples you've given from your fantastic collaborators, but what is the coolest application of metamaterials you've seen? And I don't think they mean those cooling, helping climate change.
I was going to say that. What do I say now? Oh, right. Let me just not. Looking back, I think that the perfect lens was the things which surprises me most. It was, I mean, with some ideas, you really have to labor very hard if you're experimentalists in a laboratory as a theorist, working through reams of stuff, to say that it is so, or to arrive at that conclusion. The perfect lens was a morning's work, so it was jolly good value for money. Richard, you undervalued me. You said my paper had been cited 3,000 times. It's been cited 12,000 times.
But who's counting?
All for a Sunday morning. Value for money.
Yeah, that's amazing. Encouraging us to keep our mornings precious for science and research. So thank you so much. Thank you for answering all of those questions, John. It was absolutely brilliant. We're now out of time, so I have to thank you once again, firstly to Professor Sir John Pendry, and also to everyone in the room. And I'm inviting Professor Mary Ryan, Vice Provost for Research and Enterprise, and Armourers and Braziers Chair in Material Science, to provide the closing remarks. You can stay here.
Well, thank you so much. I am also conscious I'm the only thing standing between all of you and a glass of wine, John's favourite beverage. What a state of matter. I think everyone in this room will have been, touched by not just how remarkable a scientist you are, as evidenced by this lecture, but what a truly remarkable educator as well. And the mark of a true educator is someone who has taught us all something new, and you probably all have learned something new, but also left us with questions, technical questions and philosophical questions. Luckily, there's going to be lots of time to discuss those right after the lecture, but also there should be questions you take away with you. And I think that's a really important part of what we value here at Imperial College, that we are driving curiosity, enabling people to ask the hard questions. In my role as Vice Provost, I spend quite a lot of time talking about missions and challenges and global efforts, things that we know we need science and technology to address. And I regularly have to remind both myself and colleagues that we're only able to do that when we build on really strong foundations of discovery science. That ability to ask the really hard fundamental questions and give our scientists and academics and students the time and the freedom to do that kind of work and actually to recognize that it's valued and important. I don't think anyone could have predicted the impact of the work that you were doing early on, John. It's what Flex would have called the usefulness of useful knowledge. No, the wrong way around. The usefulness of useless knowledge. How do we even begin to think about where discoveries are going to take us in 5, 10, 15, 20 years' time? And that's why it's critically important that places like Imperial continue to protect and value that kind of work. I am, as you said, a material scientist. One thing about John, and when you see him present, is just how humble he has been about the remarkable achievements. This is a truly remarkable and disruptive way of thinking. Nobody was thinking about this when you started to do this work, that actually the properties of the material could be governed not by the atoms, but how you had assembled them. Actually, if you take yourself back 30 years ago, we would not have imagined we would be here today. So we appreciate your modesty, John, but we also congratulate you on the really amazing thinking and thought leadership that you have developed in this space. If you have enjoyed this lecture, I should also give a shout out. There's another brilliant physics lecture on tomorrow, Richard, and Will Branford's inaugural lecture, same time, but in the Blackett Lab, so please join us there. I would just take a moment to say a couple of thank yous. Thank you to the Dean of Fonds who sponsors and supports this event, and it's really become, I think, a not-to-miss event in the calendar. Join us again next year. Jess, for your brilliant support, and also Emma. Where's Emma, who's done all the organising? Thank you, Emma, for doing a remarkable job on this. It just remains for me to thank Sir John again. A remarkable career. We are privileged to have you as a colleague. A really brilliant lecture. We've all enjoyed it, and we're all looking forward to joining downstairs for the research showcase and networking drinks. Please join me in showing your appreciation.
Yeah, thank you. Good.